Hello. So in this video, in this final part of the vectors chapter, we'll be looking at modeling with vectors, particularly with scenarios where we're dealing with distance or speed, right? And in you'll look at that more in mechanics, but you'd still need to know a bit about displacement, velocity, and stuff to do with that sort of stuff, right? With distance and speed. You will still need to know that for this section here. But again, you would have seen it in mechanics. If you haven't already, we'll be going over it now. Okay, so let's first talk about displacement or distance. So consider this scenario. Consider we have a point A here, let's say, and then a point B here, right? And then imagine a person, right? Right? Starts at A and then they walk, if you connect the path from A to B, right? A to B there. Then they walk along this line, right? And then we end up at point B, right? And so the distance then would be the total length they travelled, right? Let's say that is, if we get rid of the people now, let's say that this person walked 10 metres, right? Distance is, say, 10 metres. Now, now let's consider the scenario where we have now a point C down here, right? Um, and this is also going to be 10 meters, right? Actually, let me readjust this. So let's say we have the point A here again now, and then we have a point C down here. And so here again, there's a person at point A, and there's a person, and then they walk to point C, right? So they walked from A to C. Let's say again the length between A and C is 10, right? So then the distance would then be 10 as well here. Okay, so you can see then in either scenario, if in this first scenario, right, from A to B, the distance is 10 between those 2 points, and it's also the same distance of 10 from A to C. But so we go from A to B and A to C that way, but the scenarios are different, right? If we just physically just looked at the number for the distance, it's 10 meters either way. But as you can see, the two journeys are different. One's going upwards and one's going downwards, right? Um, so there's a bit of a problem because the distance isn't telling us the length, the sort of the direction, right? It's only telling us the physical length. So not exactly what the journey looks like in terms of their direction, where they're going, right? Okay. This is where displacement comes in, right? Now, let me then consider now horizontally, right, from A to B. Let's say this distance is 8 meters, and then they went up by 6. Then we can split up this overall length horizontally and vertically, right? So they walked 8 meters and 6 meters, right? And overall, if you did do Pythagoras, you would get 10. Okay, so this is fine. But okay, so then if we split it up horizontally, so they walked forward by 8 meters and then upwards by 6, right? Now we're starting to get somewhere because now we're starting to include this sort of notion of direction, so forwards and upwards, right? Um, but actually, then if we use I and J notation, so remember I and J are just sort of the I is basically the x direction or the x axis, and the J is basically like the y axis, right? So if we then use I and J, eight, 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 8 steps or 8 units forward is going to be 8i, and then at 6 upwards would be positive 6j, right? So therefore then I can actually then give this sort of line from A to B, the direction from A to B, by this vector here, 8i add 6j. And now that's going to incorporate my sort of direction, right? And so then this vector is what we call the displacement, right? And so the displacement tells me from 2 points A to B exactly what direction I need to go. So firstly, I need to go A to I, so 8 across, and then 6J, meaning 6 upwards, okay? And I get to the same point, okay? So that's, therefore, then we can decompose it into I and J, so X and Y, and then we can get the vector, okay? And actually then, if we did the same for this journey here from A to C, let's say again that's 6 downwards, so that'd be minus 6J now, because negative, because it's going downwards. And then going to the left by minus 8I, okay? So, because again, I and J, if it's negative, that's because it's going in the negative direction, so left, okay? Like the x-axis, right? And so then the vector in this case is going to be minus 8I minus 6J, right? And therefore this is my displacement in this case. So the displacement is the vector for the journey, okay? So hopefully now we've got a much better picture using the vectors for what the journey is like in terms of, well, how far forwards or backwards you're going, and then how far up and or down you're going. It incorporates the direction as well. And so then you notice, hopefully you notice then, that whilst the distance is the same in both journeys, the displacement vector is different, okay? Because in this case, the negatives indicate they're going in opposite directions. So that's the whole idea of a displacement, right? It's the vector. It's a vector that tells me the direction to go from one point to another. Okay. So lastly, to reiterate, 8I and 6J would be 8 across, as you can see here, and then 6 up, and then we end up at the point B. Okay. Okay. Right. So if I was to summarize this then, displacement is the vector for the how should I word it? Displacement is the vector for the, I guess, route between 2 points. So what I mean by route is from point A to point B. The route is how do I get from point A to point B. Okay. So in other words, it tells us how to get from point A to point B. Right. Now, I did kind of hint at this earlier, that I said that the what's it called? The Pythagoras. So, in other words, if you did the hypotenuse, right, of this right angled triangle, if you did 8 squared and 6 squared, you would get back 10, which is coincidentally the distance. Well, actually, then, if we then confirm this, if I did then the magnitude of my vector, 8I and 6J, so the magnitude of my displacement, if I did that, then that'd be root 8 squared or 6 squared. And then I will get 10. Okay? But coincidentally, 10 is my distance. And so actually then, another cool feature for displacement is actually, if we then do the magnitude of my displacement vector, it tells me the distance. Okay? And so therefore distance, I would say, is the magnitude of displacement. Okay, and that distance, tells you what you expect. It just tells you the physical distance or the length from one point to another. Okay, but displacement tells me the vector for the direction or how to get from point A to point B. Okay, right. Okay, so that's distance and displacement. Now we're going to look at speed and velocity, and it's pretty much the same sort of story. Okay. Right, so let's say, let me then copy down my A to B, right? Now let's say then A is the point 0.21 and b is the 0.107, right? And obviously then the length would be 10 still. If you did the distance between 2,1 and 10,7, it will still be 10, okay? And again, the change in x, right? The change in x then between 2 and 10, that would be 8. And the change in y from 1 to 7 would be 6. So it's the same journey, right? It's still 8 across and 6 up, right? But now I want to talk about velocity, right? Oh, well, actually, before we talk about velocity, let's look at speed, right? So speed. Let's say the speed of someone walking. Let's say, for example, speed is. Actually, I'm going to do it down here. Let's say, okay, that speed is of someone is 5 meters per second, right? What that means is then speed tells us, and you can kind of look at the units to help you here. Speed is kind of a rate. It tells me how much they're moving per second, how far they're traveling per second, or per minute or per hour. Depends what the unit for time is. In this case, keep it simple, meters per second. So every second, that's telling me they're walking 5 meters. So let's say there's someone here starting here, and then after 1 second, the speed of 5 meters per second tells me they move 5 meters, okay? Then another second later, then 2 seconds, they move another 5 meters. Then if they keep this up, okay. And so overall, then every second they move 5 meters. So overall, then say for the whole 1 second there. Overall, then for 2 seconds, they would have moved 10, right? 10 meters, right? So then what we can say then is this then coincides with the speed distance time formula, which you should be very familiar with from GCSE, and that is distance is speed times time. Okay. And again, we will be using that in this section. It might be a sort of basic formula, but you still need to remember it, okay? Right. So hopefully you get the idea of what speed is, right? The speed tells me how much I'm moving every second or every unit time, okay? Right. Velocity is basically the same, but it's in the vector form instead. So let's revisit this example here, okay? Where we're moving from point A to point B, there. Now, let me then say it's moving with velocity. So, for example, the velocity of this journey from point A to point B is the vector 1.5 or 2i add 1.5j meters per second, okay? Let's say my velocity is this. It's this vector here. So again, velocity is going to be the vector for speed, which we'll see in a second. But the velocity, let's say the velocity is 2i and 1.5j. But what does this mean, right? In terms of this journey, if I'm moving from point A to point B, from point 21 to point 107, and I'm moving 8 across and 6 up overall, what exactly does this velocity mean? What that means is, and again, it's analogous or very similar to this speed example, right? With velocity, it's the same thing. It's telling me if I'm starting at point A, it's telling me I need to move by this amount, by this vector every second. So I'm going to add this vector on to the point every second. So let's demonstrate what's going to happen. So I have the point A here. And that is as a vector then 2 1. Actually no, let's keep it the point 2 1, right? The point A is 2 1. Now the velocity is telling me I need to move by this amount every second, okay? So if I'm starting at 2 1, I'm adding 2i and 1.5j. So again, the I is basically the x, and the 1.5 is basically the 1.5j is basically the y, which means say after 1 second, I'm at the point A1, right? So then, actually no, I'll do it down here. A21. Okay, we start at A at 2, 1. Now, after 1 second, we're now at the point A1, okay? Which means we need to add this amount on 2i 1.5j. So we're going to add 2 to my x point, right? Because 2i is basically 2 lots of x. So 2 is originally the x value. So I'm going to add another 2, and now I'll be 4 for x. And originally y is 1 at A. So now I'm going to move by 1.5. So now it'll be 2.5. Okay? And so after 1 second, I'm now at this point A1, this coordinate here. So that is the whole idea with velocity. I'm moving my point, right, by this amount, right, by this velocity. The velocity tells me how much I need to move my point by every second, okay? If I was to continue this on then, let's say now I'm at the point A2, right? And then I'm going to do the same. So from this point at A1, I need to add another 2i and 1.5j. So 4 add 2 to my x will be 6. And 2.5 add 1.5 would be 4. Okay? I'm going to do the same again then. So now I'm at the point A3 after 3 seconds then. So again, I'm moving every second. I'm increasing by my vector, okay? So at the third point, after 3 seconds then, again I need to add 2i, so 2 add 6 would be 8. Then 1.5j will be 4 add 1.5, which would be 5.5, okay? So now I'm at this point. Now, after 4 seconds then, so now I'm at A4, if I add another 2 on, so 2 add 8 would then be 10, and 1.5 for y, add by 5.5 will be 7. Okay? Well, okay, so what do you notice about this point now? 10.7. I'm now at the point B. I'm now at my destination, okay? This is now also point B at 10.7. So now I've done my journey, okay? So that is the whole idea with velocity then. The velocity tells me how much I need to move per second, okay? So hopefully you can see that, right? And eventually it gets to my destination after so many seconds, okay? If I keep adding by that amount. Right, so again, the crucial difference then between velocity and displacement is displacement gives me the overall vector from A to B, right? If I look at this again, if I look at this again then, so my displacement from A to B here is just 8i and 6j. That's the overall journey, right, from A to B. But my velocity, because it's per second, it tells me how much I need to move every second or for every unit time, okay? So that's the difference, but that is velocity, okay? And so therefore, velocity is a vector again. So velocity is a vector which says how much I need to move by every time t, okay? It could be seconds. If it's meters per second, it could be per minute, it could be per hour, it could be whatever unit we want, okay? But for every unit, every time t in general, okay? And again then, the speed then, is going to again be the magnitude of this, okay? So if I was to work out with this velocity then, this velocity vector, the speed then is going to be the magnitude, right? So it's going to be the magnitude of 2i add 1.5j. If I do that then, that'd be root 2 squared add 1.5 squared. If I do that in my calculator, I get 2.5, and then that would be meters per second, okay? And therefore, because that was 4 seconds, right? If we were then to do my speed times time, so 2.5 times 4 seconds, that indeed gets me 10 meters, which again, as we saw, 10 meters what's the overall distance, okay? So we do get distance if we do speed times time here. So there we are. So again then, I will also add again that the speed is the magnitude of velocity. And from now on, this is kind of how I want to think about velocity, speed, distance and displacement, okay? And so there we are. So in summary then, the displacement is the vector that tells me how to get from point A to point B. The distance is the magnitude of displacement, which is the overall distance, or the length of the journey. Velocity tells me how much I need to move by every second, for example. And then speed is the magnitude of velocity, okay? Right. Okay, so before we look at some, I guess, more serious examples, I want to really just hone in on this concept of distance, displacement, speed, and velocity with these two questions here, just to really reinforce what we've learned, okay? So, we need to find the speed and distance travelled, so speed and distance, when firstly, our velocity is this vector minus 3i add 4j. So as a column, we can write that as minus 3 plus 4, there we are, meters per second, okay? And by the way, we can express meters per second, we can change the unit to ms minus 1 instead. That's the more formal way. And it is equivalent to meters per second because s to the minus 1, if we use our index laws, that's just reciprocal, right? 1 over s. And so what this is saying in meters per second is technically meters over speed, or seconds, sorry. So they are equivalent, right? But get used to this sort of notation where we do meters per second to the minus 1, which is the reciprocal, right? But either way, that's our units, meters per second. Okay, we're also told then that the time is 15 seconds. But, okay. Okay, so firstly we need the speed. Well, the speed is the magnitude of velocity. Okay? So the magnitude of this vector, minus 3, 4. Okay? So then if we did root minus 3 all squared, add 4 squared, that would get me, if I did that in my calculator, 5, okay? And then that'd be 5 meters per second, okay? Don't forget your units. So then my speed is 5 and my time is 15. Therefore my distance then, remember distance is speed times time, is going to be 5 times 15, which would be 75 meters, okay? And there we are. Okay, part B, I'll do it down here. My velocity is now 2i add 5j, or as column 2, 5, okay? Therefore, my speed then is going to be the magnitude of this, which should be root 2 squared add 5 squared, which would be root 29, okay? And that would be in meters per second. Okay, so that's my speed. I'm also given the time now is 3 seconds, okay? So therefore my distance then is going to be speed times time. So it's going to be root 29 times 3, which is just simply 3 root 29. So I guess if I round it then, so that'd be meters. If I was to round it right as a decimal, that's 16.2 meters to 1 decimal place. And so that's it then. So hopefully you get a flavour for using distance, speed, time. Again, that crucial formula from GCSE. And also starting to realise we can go from velocity to speed. So we can go from the vector to the magnitude, okay? And that the velocity is the vector and the speed is just the number, okay? And we call that a scalar technically again. So you might see the word scalar floating around. Speed is just a number, it's the scalar. But velocity is a vector, okay? Right, so there we are. So we're going to look at some more examples now. Okay, so we're starting with this question then. So we are told a girl walks 2 kilometers due east from a fixed position O, so origin, right? O to A. And then 3 kilometers due south from A to B. Find firstly the total distance travelled. Okay, so let's kind of plot the points then. Let's plot what's happening here, because it's quite geometric, right? So very helpful to draw what's happening. Right, so first of all, it's talking about east and south, right? So again, you do need to know your compass directions. So obviously we go from north here. That's sort of like the positive y-axis, right? And then east, which is basically the positive x-axis, right? Then south, which is the negative y-axis, right? And then west, which is the negative x-axis. So you can think of these as the four quadrants, right? North, east, south, west. Anyway, so we are told this girl walks 2 kilometers due east. So imagine we have our origin, say here, O. Then 2 kilometers east will be 2 kilometers to the right, okay? The east direction, okay? Then that's the point A, okay? That's 2 kilometers there. Then we are told she then walks 3 kilometers south from A. So that's going to be down by 3, okay? And then we are at the point B. Okay, cool. So we are then told to firstly work out the total distance travelled. Now, very, very common pitfall, I imagine a lot of people will do. They would probably then connect O to B in this way. And then they'd probably do Pythagoras to say the length is the hypotenuse. But that's not what the question's asking. You need to pay attention to the question. Because they're asking the total distance travelled. They did not say the distance from O to B, okay? Yeah, pay attention to the wording. Total distance travelled is how much she actually travelled, okay? Not from one point to another, but how much she actually travelled. So she actually walks 2 kilometers east and then 3 kilometers down. So the distance she travelled was 2 kilometers add 3. So very simply, total distance is 2 add 3. Right, which should be 5 in kilometers, and that's your answer. Okay, make sure you do pay attention to the wording. Okay, so it's not the length here, it's not the hypotenuse. Okay, then part B then says find the position vector B relative to O. Right, so in other words, the position vector of B relative to O, that's the vector from O to B. That's going to be this line here then, right? O to B as a vector. So then remember that this vector, position vector B, is basically O to B, right? O to B, right? Remember when we looked at position vectors, it's basically the vector from the origin to the point B, right? And so again, because it's a vector, it's going to look like AI add BJ, right? There's going to be some lots of I and some lots of J. So we need to consider the I and the J components, or remember, I and J are basically X and Y. We can split up the vector in terms of X and Y, okay? So, well, we've actually got this already. O to B, but then you can think of it as we're going 2 across, right? We're going 2 that way, that'd be 2I. Right, then we're going down by 3, so we're going down here. That would be negative 3j, right? So then our vector then is simply going to be 2i minus 3j then, right? And that's it. So again, it's very handy that if we need to find a vector or something like this, we can split up the vector into the I and the j part, or the x and the y part, okay? In this way. Now part C then says to find the magnitude of O to B. So now that we found the vector OB, we can find the magnitude of that by doing the root of 2 squared add minus 3 squared. And then if we do that, we get root 13. Okay, and there we are. Then part D then says to define the bearing of B from O. So again, bearings then, again from G to C, and we looked at bearings earlier on in the course as well. But bearings, as a brief reminder, is an angle, but the key idea of a bearing is we measure from a north line, so upwards like this. Then from the north line in here, then we measure an angle around it in this way. Okay, so for example, if we had a bearing of, let's say, 135, well, first of all, it'd be 90 degrees. That'd be a 90 degree. Then we need another 45, right? So 90, and then this angle 45. If we add these two together, we do get 135 overall. So the overall angle then, if we just combine them, from the north line, that angle 135 will be our bearing, okay? So that's the whole idea. With bearings, we measure from the north line, so from the top, okay? Okay, so in this case then, the the bearing of B from O, so it's from O, from the origin, so that's where we take our north line, and then we go to B, okay? Well, if we measure the angle then, it's that whole angle there, okay? But actually there, because again, split this up into two different angles. We've got a right angle then, of 90, and then we've got this angle theta as well. Combine theta and 90, we get the bearing from O to B. So then the mission basically is to find the angle theta. But actually, we've got a triangle, haven't we? Right? If I have the triangle here, the triangle OAB, O to A to B, if you just consider the lengths, right? We have 2 that way, then 3 downwards. And we also know the length O to B is root 13. That's the length here, right? So then to find the angle theta, and given that this is going to be a right angle, right? Well, we can just use SOHCAHTOA, right? Really, we can use SOHCAHTOA to find theta. And actually, let's use tan theta, right? So theta is opposite the side 3. So therefore, tan of theta is going to be opposite, which is 3, over the adjacent, which would be 2. Okay, then if we do inverse tan, we get theta to be uh, 56.309 blah 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 degrees. Okay, cool. So then therefore then the bearing then, if we go back, the bearing from O to B is again the whole angle here, the 90 degree right angle and theta. So it's going to be 90 add theta, right? So bearing from O to B is going to be 90 add theta. So 90 add this 56.309, which if I do that is 146.3 degrees to 1 decimal place. Okay, and there we are. Okay, cool. So again, make sure you are comfortable with bearings as well. I've noticed a lot of questions with vectors to do like the throw-in bearings. Just remember how to measure bearings, right? Very simply, it's from the north line up here. Then we measure clockwise, so we measure in that way. Okay. Okay, cool. Okay, let's have a look at another question then. So it's a very similar style question, but it's a bit more of a step up, right, than the last one. So have a look at this one then. So we're told in an orienteering exercise, a cadet leaves from the starting point O and walks 15 kilometers on a bearing of 120 to A, the first checkpoint. From A, he walks 9 kilometers on a bearing of 240 to the second checkpoint at B, and then from B returns directly to O. So again, there's a lot of information here. There's a lot of like geometric stuff, like positions. So let's again draw and plot the situation, what's going on here. So again, we're starting an origin. Let's call that O again. Now, we are told from O, the cadet walks 15 kilometers on a bearing of 120. So the bearing of 120 means, again, if we measure from the north line then, from O, if we measure the 120 angle, right, it looks something like this, right? So we're going to have 90 degrees, first of all, right? Then we're going to need another 30 degrees, right? Because then 90 add 30 gets me 120. Okay, so then therefore, we're going to be along this line here then, right? So we can extend this line then to the length of, say, 15. And then that'll be my point A, right? Cool. Right, so that'd be 120. Then we are told from A, he walks 9 kilometres on a bearing of 240. So again, then if you do the bearing of 240 then at A, so again we have a north line, then 240, well 180, right, would be halfway here. So we need another 60 degrees. So it'd be something like this, right, another 60. So 180 and 60 will get me 240 overall. So, okay then, so if we do the whole angle then, that would be 240 at A. So then we go along this line here for, what is it, 9 kilometres? Yes, 9 kilometres, and then we reach the point B, okay? Then we're told from B, he returns to O. So at that point, we can just connect B back to O in this way. And there we are. And again, you can start to see a triangle emerge now. Okay, cool. So this is our situation. This is our diagram here. Cool. Then we are told then, for part A, we need to find the position vector of A relative to O. So we need to find the vector O to A, right? That line O to A. That vector there. So again, a vector is going to be is going to look like AI at BJ. So we're going to need to find the I and the J component or the X and Y component. Depends how you think about it, right? It's the same thing virtually. Well, actually, because we're going to think about the I and the J part of O to A, right? Well, then let me consider drawing this triangle. Then let's sort of decompose it into X and Y. So in other words, if we're going from O to A, we could split it up to the X part here, and then we can go down to, by the Y part. So if I get rid of the north line there, we've effectively got this equivalent triangle, right? From O to A then, we can also go X in the X direction here, X here, and then down in the Y. So I've got the X and Y part of this vector here, O to A, in this red triangle here. Okay, cool, and it's going to be a right angle there. Right. Well, actually, at that point then as well, hopefully you can notice then this 120 degree angle here, we can again split that into 90 degrees, and then the angle in this triangle here of 30, right? And overall that'd be 120. Well then hopefully you can spot them. We've got this triangle here, right? We've got this right angle triangle. So we're starting at O. And then we end at A. So then the vector O to A then, we can go, it'd be X and Y, right? Well then we can, and we know this angle is 30. But we also know the length of O to A is 15. Well, again, then we've got an angle, we can use SOHCAHTOA, right, to find the X and the Y part. So, if we were to proceed with that then, and let's do it in black, firstly, the angle 30 is opposite Y, so it's going to be sine. So we can do sine of 30 is going to equal the opposite, which is the Y, over the hypotenuse, which is 15. So therefore, Y is going to be 15 sine 30. And then if I do that, I get the Y to be 15 over 2. Cool. And then likewise then to find X, well X is adjacent to the angle. So then cos 30 is going to be the adjacent, which is X over the hypotenuse of 15. So therefore X is going to be 15 cos 30, sorry. Then if I do that, I get X to be at 15 root 3 over 2. And so therefore then, the x and y part are there. We can, so, if I then add this on, x and y, well then x is x was 15 root 3 over 2, right? And then the y part was 15 over 2, okay? So then we can see the vector then, the vector here, O to A, if we go along x and then down by y, the vector, the I part is 15 root 3 over 2, right? That is a root 3. 15 root 3 over 2i. So O to A is going to be 15 root 3 over 2i. And then the j part, well, it's 15 over 2j, but it's going down, so it's negative, right? The negative direction, so negative 15 over 2j. And that's my vector, okay? Cool. So that's my position vector A, okay? So again, like I said, a very handy tip is to, if you want to find a vector in this way, you can just consider splitting it into the x and the y part, okay? Then you find x and y, you get the I and the j part in this way. Okay, then we're told for part B to find the magnitude of the vector O to B. Well, that's going to be, O to B is this vector here, so the magnitude is going to be this length here, right? So the magnitude of O to B is this length of this triangle here. Now notice we weren't asked to find the position vector of B, so we weren't asked to find the vector OB. We're only being asked to find the magnitude of it, which means it's kind of saying there's a way we can find the length of it without having to find the vector itself, right? So how are we going to do that? How are we going to find the length of this side here? Well, again, notice we're working with a triangle, right? The triangle in black. We can perhaps use some trigonometry to find this length here. So if I call, so again, this is going to be then, if this length is going to be magnitude OB, right? This length here. So how are we going to proceed with finding this then? Well, we've got two sides already. We've got the side 15 and the side 9. And we want to find the third side. I'm thinking cosine rule, right? Because remember, cosine rule is dealing with all three sides, right? But I also need an angle then, right? How am I going to find an angle? And in particular, because I want this side here, this side here, I'm going to need the angle opposite to it. So I'm going to want that angle here. This angle here, I'll call theta, right? So I want to find theta. Once I find theta, then I can use the cosine rule, okay, to find this length of OB here, okay. Okay, so how am I going to find theta then? Well, then I can stare at what's going on here with all these angles. So I've got this reflex angle 240 right here. I've also got the angle theta here. Well, actually, if I can then find this angle in this red triangle here, right, then I've got angles around the point A. Angles around the point have to add up to 360, right? So if I can then find all the angles here, so if I find the angle in the red triangle here, then I can take that away from 240, right, to get the remaining angle theta here. So how can I find this then? Well, actually, I've already done the hard work, because I know that this angle's 30 and I've got a right angle of 90. Well, I know angles in a triangle and have to add up to 180. So this angle here is just going to be 180. Take away 30, take away 90, take away the other two angles, right? If I do that, I get 60. So this has to be 60 degrees then. Hopefully you're with me there, right? So in this red triangle, this angle here has to be 60 because the other two angles are 30 and 90. So if I take them away from 180, I'll get 60 left, okay? That's the idea, okay? Now, I've got this angle 60 then, and I've got angles around a point. So that means theta has to be 360, take away 240, take away the angle 60. If I do that then, I get theta to be 60. Okay, cool. So I can fill this in then. So now I know that this angle has to be 60 here as well. So then I'm now in a position I can use the cosine rule on my black triangle, right? So I know that this length is 15. I know this length is 9. I know I've got the angle here of 60. That's opposite the side I want. So therefore, if I use cosine rule, I can say that the length of OB, so the length of OB, which should be squared, would be the other two sides, all squared, so the 15 and the 9. So 15 squared add 9 squared, take away 2 lots of 15 times 9 times the cosine of the angle 60. So if I do all of that, I get the length squared would be 171. And so therefore then the length by itself is going to be the root of that, right? So if I root that, my calculator gives me the answer 3 root 19. So that's simplified, okay? And there we are. So that's my length. Cool. Then part C then. And actually I can add that on then. This length now, O to B, the length is 3 root 19 here. Cool. Now part C is asking for the bearing of B from O. So again, the bearing from O, so the north line at O, which we've already drawn. And then from the north line at O, we need to get to B. So it's going to be this whole angle here, right? So it's going to be this angle 90, this angle 30, and this extra angle here. I'll call it alpha, okay? So hopefully you can see then that the whole angle here, the 90-degree angle, the 30, and the angle alpha, overall gets me the bearing from the north line from O to B, okay? So how am I going to work that out? Well, I just need to find alpha then, right? But actually, I'm in a position now in my black triangle. I got all three sides. I've got 15, 9, and 3 root 19. So to find the missing angle, I can use cosine rule again. And the angle alpha is opposite the 9. So therefore then, via the cosine rule, cosine of alpha is going to be the other two sides. So 3 root 19 and 15. So 3 root 19 all squared. Add 15 squared, take away 9 squared. Divided by 2 lots of 3 root 19 times 15. And then if I do that, I get cosine of alpha to be 7 root 19 over 38. Right, okay. So therefore alpha then, if I do inverse cos, I get 36.6 degrees, right, to 1 decimal place. And there we are. So that's alpha then, but that's not the bearing. Because remember again, the bearing from O to B, from the north line, is the whole angle here. So it's the alpha and the 30 and the 90. So I need to add 30 and 90 onto this to get the bearing. The bearing from O to B. That's going to be 90, add my 30, add the angle alpha. So 36.6 gets me 156.6 degrees to 1 decimal place. Oh, okay, part D then, the last part of this. We need to find the position vector now of B relative to O. Right, so the position vector again is the vector literally O to B, right? So again, it's this line here, effectively, the line from O to B. We need that vector, okay? Hopefully you can see the diagram starting to get a bit cramped now, but hopefully you can see it's just this vector here, O to B, in my triangle here. How am I going to find that then? Well, again, to find the vector, I can consider the x and the y parts. So if I do it down here then, okay, so if I draw, again, this situation then from O to B down here, right, again, from O, remember I had a north line here, right? So then the angle then, the overall angle has to be, if you think about it, the bearing, it's the bearing in part B, right? That we worked out. Part C, sorry. The bearing is the angle from O to B, right? From the north. It's 156. So actually, our sketch is a bit off. So 156, well, that would be 180, right? So therefore 156 would be a bit less than that. So it'd be somewhere there, okay? So B would actually be over here. But that's fine. We can just adapt our diagram. So 156 is my bearing from part C, right? So therefore we can split it up then to find the vector O to B. We can again split this up into the I and J part, right? Again, it's going to have an X part and then a Y part. And again then, you can see then that this bearing of 156, right, the angle from O to B in this way, we can again split it up to a 90 degree angle. And then the angle here has to be 156 take away 90. And then that angle is going to be 66.6, right? And so there we are. So now we can see we've got a triangle, but we also know the length O to B. We know the length. We did that in part B, right? The length O to B was 3 root 19. So then, because and this is a right angle, so now we're in a position we can find the x and the y part from O to B, right? Okay. So therefore, then we can use some Sokotoa. So, okay. So firstly, y. Well, y is opposite the angle 66.6. So sine of 66.6. It's going to be y over the hypotenuse, which is 3 root 19. So therefore y is going to be 3 root 19 lots of sine 66.6. So if I do that then I get 12.001. So I've round that to 12.00, okay, 1 decimal place. Likewise then I can find x. Well, x is adjacent to the angle, so cos of 66.6 it's going to be the adjacent, which is x over 3 root 19. So therefore x is going to be 3 root 19 lots of cos 66.6, and so that will get me 5.19 blah blah blah, okay. But therefore then we can deduce then that the vector O to B, well, the I part, right, the I part is the x part, and it's going to the in the positive, right, so it's going to be positive 5.19. I'm going to round this to 5.2, right, 5.2 for x, I. And then we're going down by y, so the j part of this is going to be negative 12, okay? Negative 12j to 1 decimal place. And there we are. So that's my vector O to B. So again, very handy to consider. You can split it up to the x and the y part, okay? And so you can construct the triangle by considering the angle we have and the length, to then use Sokotoa to find the x and the y part. Okay. Okay, so then we got some more exercise questions then. So we've got this one first of all. We did an example like this last time, very similar, but again, it does come up time to time. So it's a good question to practice. So we've got this question then, and we're told a diagram shows a sketch of a field in the shape of a triangle. Given AB is 30i and 40j, and AC is 40i minus 60j, find B to C. So the vector B to C here. Right, so, okay, well, we're given AB, so that vector here, and then A to C, so there we are. Well, then to find BC, we can go, well, obviously there's no direct way. There's no direct way because we don't have any information about BC. So we can go around the triangle, right? So we can go from B to A, then A to C. Well, B to A, well, we know what AB is that way. So BA is going to be the other way, so it's going to be negative AB. Add AC. Right, and then AB, well, we know that AB is minus 30 and 40j, so it's going to be minus lots of 30 and 40. Remember, we can convert to column notation with I and j. Then AC is the vector 40i minus 60j, so 40 minus 60. Oh, so then if we add these vectors, we get minus 30 add 40 be plus 10, minus 40 minus 60 be minus 100. And I guess then as I and j, it doesn't say, we'll be fine with leaving it as a column because it doesn't specify what the answer needs to be in. But in terms of I and j, this will then be 10i minus 100j. And there we are. Okay, then it says for part B to find the size of angle BAC, right? So the angle is at A because A is in the middle, so I'll call that theta, right? Well, again, we're in the position where we know the vectors for all three sides, A, B, B, C, A, C, right? What we can do then is we can find the magnitude of all the sides, okay? But the magnitude of all the vectors to find the length of all the sides. If we were to proceed, so I'll do it up here then, right? So, part B, so what we're going to do is then find the length of all the vectors. So firstly, AB is the vector 30, 40. So therefore the magnitude of AB is going to be root 30 squared add 40 squared, which would be 50, okay? And then we can add that on. So the length AB is 50 here on my triangle. Then A to C, we're given to be 40 minus 60. So therefore the length of AC is going to be root 40 squared add minus 60 squared, which would be 20 root 13. Okay, so if we add that on, 20 root 13 here, there we are. Okay, then the remaining side is BC, right? Well, that's what we found in part A. The vector BC is 10 minus 100. So therefore the length of BC is going to be root 10 squared add minus 100 squared, which would be 10 root 101, okay? Cool, so now we've got all three lengths. So hopefully you can see that this now just boils down to a trigonometry problem. In particular, we're dealing with three sides and an angle. That's going to be the cosine rule, right? And so in general, that's the sort of idea with these sort of shape questions, or if it's asking for size or lengths. Usually they give the sides as vectors, then you can find the length of every vector to find the length of all the sides. From then it becomes trigonometry. Right, so the cosine rule for theta, well, theta is opposite this length, 10 root 101. So if we were to do the cosine rule for theta, well, cos theta would be the other two sides, so 50 and 20 root 13. So 50 squared add 20 root 13 squared, take away 10 root 101 squared, divided by 2 lots of 50, 20 root 13. And so if we do this, we get cos theta to be minus 0.3328 blah blah blah. So therefore theta then, if we do inverse cos, we get 109.44 degrees to 2 decimal places. So that's the angle. Oh, to 1 decimal place would then be just 109.4. Okay, to 1 decimal place. Okay, cool. So that's the angle there. Okay, then part C then says find the area of the field in square meters. So the area of this triangle. Well, we know what theta is now. This 109.4. So we can use half AB sine C with the angle here. So okay. So the area is a half AB sine C. Well, the angle C is this theta, right? 109.4. So the two sides next to it are A and B, 50 and 20 root 13. So therefore the area is a half times 50 times 20 root 13 times by sine of 109.4 degrees. So if we do all that then, put it in a calculator, we get exactly 1,700, and that'd be in square meters. So meters squared there, and that's our units. And there we are. So again, so hopefully once you realise you can just find the length of the vectors by using the magnitude, then it becomes a more straightforward trigonometry problem. Okay, and that's the whole idea, to find to find the sides, the length of the sides by using the magnitude of the vectors. Okay. Okay, so we've got this question now, and this question will use ideas of velocity and displacement that we looked at the start of the section. But we are told in this question a boat has a position vector of 2i and j kilometers, and a boy has position vector of 6i minus 4j relative to origin O. First of all, from the distance from the boat to the boy. So again, we're going to probably sort of plot where these points are, right? So position vector basically means coordinate, right? A coordinate from origin, right? So 2i and j is basically 2, 1, right? Basically. So if we have an origin, let's say here, then 2, 1, 2 across, 1 up, there, okay? That would be my boat, okay? Boat at 2, 1. And then the boy is the position vector 6 minus 4, so that's basically coordinate 6 minus 4, right? So then if I go from the origin, that's 2 across, another 4 across would get me 6 overall, right? So then if I then go down by minus 4, right? 4 down, I'm now at this point here, and that would then be my boy, okay? At the point 6 minus 4. So firstly then, the distance from the boat to the boat from the boy, so if we then just, connect the 2 points, the distance between the boat and the boy is basically the length of this line, essentially, right? Well, we've got these 2 points, 2, 1, 6 and minus 4. Isn't the distance between the 2 points, right, the length of the line? So then we can use our distance formula between 2 points that we looked at in the straight lines chapter, right? So then the distance then from the boat to the boy, it's going to be the distance from point 2, 1 to 6 minus 4. So it's going to be the root of change in x. So we have 6 here for x. Take away 2 from the boat. So take away 2 all squared. Then change in y squared. So it's going to be minus 4. Take away 1 all squared. Then if we put that in a calculator, we get root 41 all squared, okay? And the units are in kilometers, okay? Cool. Right, and then part B then says to find the bearing of the boat from the buoy. So we're from the buoy, we measure the bearing. So remember, then we have a north line, right? So then the bearing is this whole angle here, this reflex angle theta here. Well, what we could do really to find the angle theta, then the bearing, we can find this angle here that I'll call this angle theta then instead, right? If we can find the angle theta, then again we're around a point at 360 degrees. If we take that away from theta, 360 take away theta, we get the reflex angle, right? The bearing. How are we going to find theta then? Well, then again, let's sort of consider, if I get rid of this line here and extend it, what if we then do change in x, change in y? Because we get this triangle here. If we have the point, let me move this then. So boat at the point 21. So again, we're from the point 21 to the point 6 minus 4. For the change in x then, this length here in this triangle, isn't that going to be then 6 take away 2 for x, right? Then that length will be 4. And then similarly then, this length is a change in y, right? So that would be 1 up here for the boat, and then y is minus 4 down here. Overall, we've gone down by 5, right? So that length there is 5. Well, then you can spot them. You can use SOHCAHTOA, a bit of trigonometry, to find the angle theta in this triangle. So therefore, theta weighs opposite the side 4. So therefore, it's going to be, we can use tan theta, right? So tan theta, I'll do it up here actually. So we're going to get tan theta is going to be opposite, which is 4, over the adjacent, which is 5. So therefore theta is going to be inverse tan of that, which should be 38.659 blah 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 degrees. That's my theta then. So therefore my bearing is going to be 360 take away theta, right? Because then overall I get this bearing here, this angle here, right, from the north line. So therefore the bearing from boat to boat, from buoy to boat, that's going to be 360 take away theta, which was 38.659 blah blah blah, which would get me 321.34 degrees, to say 2 decimal places, right? And so there we are. Okay, now I'm told the boat travels with constant velocity 8I minus 10J kilometers per hour. It says for part C, verify that the boat is travelling directly towards the buoy. So we're starting from the boat here, right? And then we're ending at the buoy. Okay? At the buoy here. Okay? Okay, so the wording might be really like off-putting, like what does it mean by that, by verify in this way. Right, okay. So what this means, what we can say is, remember what velocity means. It's saying, well, the time is in hours, which means basically if we're starting at the point 21 here with the boat, every hour we're adding on an extra 8I minus 10J. So we're adding the vector 8 minus 10 to the point 21, right? If we keep adding an amount of 8 minus 10, right? So every hour, right? So in T hours, we can add T amounts of the vector 8 minus 10 to my point at the boat. Eventually, for some time T, after T hours, right? After we added T amounts of this vector, this velocity, this tells me I will end at my buoy, okay? So when I start at my point 21 and I add after so much time, right? After T amounts of the vector 8 minus 10, I end at the buoy, okay? So I can write this down, right? If I express it on an equation then, so I start at the point 21, okay? That's my boat coordinate. Then my velocity is, again, my velocity vector is 8 minus 10. And then eventually, after t amounts, after t hours, so I start here, then after t amounts of this vector, then I end up at my buoy. And my buoy, again, has the 0.6 minus 4. So the idea then, if indeed the boat does reach the buoy with this velocity, then there has to be a solution to the equation for this to happen, okay? Well, to solve it then, we can sort of just be solving for t, okay? We can sort of then just add these vectors on the left side. So firstly, this will simplify to 2, add 8 lots of t. So if I multiply this vector here by t, 8t, and 1, add minus 10t, has to equal the right side vector of 6 minus 4, okay? Now, I then have two equations, right? If I compare the top and the bottom part, I therefore get 2 add 8t is 6, and 1 minus 10t is minus 4. So if indeed the boat does reach the buoy, right, the end point here, right, with this velocity, there is a solution to t to satisfy both equations, okay? So let's solve it. So we can solve the top one, right? So if we solve the top one, so therefore 8t, if I subtract 2 to both sides, it's going to be 4. So therefore t is going to be 4 over 8, which would be a half. Okay, so that's my solution here. I then need to check that this would also then be a solution to the second equation here. So I'm going to sub t into this second equation. 1 minus 10t is minus 4. So therefore 1 minus 10 lots of a half for t. What will that get me if I put it in the calculator? Well, 10 lots of a half is 5. So 1 minus 5, which gets me minus 4. Great. So that equation is satisfied. So both equations are satisfied, okay? And so that means then there is a value of t, right, where we end at the buoy with this velocity, right? With the velocity 8 minus 10, it indeed does reach the buoy, right, at this 0.6 minus 4 here, okay? And specifically when t is a half, right? T is in hours, so it'd be half hours, okay? So therefore I'd say, therefore the boat does indeed reach the buoy. What was the wording? Yeah, the boat is travelling directly towards the buoy. So yes, with this velocity, if it's travelling towards the buoy, it will reach the buoy, okay, with this velocity. Right, okay. Then part D, find the speed of the boat. Now that's quite simple, because now we've got the velocity, the speed is just going to be the magnitude of that, right? So the velocity again is 8 minus 10. So therefore, my speed is the magnitude of this, right? So magnitude of 8 minus 10, which would be root of 8 squared, add minus 10 squared, which would be 2 root 41. And again, the units are important. It's kilometers per hour. That's my speed, okay? And there we are. Okay, part E, lastly, it says work out how long it will take the boat to reach the buoy. Well, actually, that's what we did in part C. We actually found that time, t was a half, right? Because that said then, after half hours, so after I removed the half lots of my velocity, when I started at 2-1, after a half lots of 8 minus 10 of my velocity, I end at 6 minus 4. So actually I've already did solve it, so t would be a half hours, or in minutes if you wanted to, 30 minutes. But if you really want, if you're not entirely convinced, right, we've already got that solution, but if you're not convinced, remember, because distance is speed times time, we know time is also distance divided by speed. We already worked out distance and speed already. because the distance we worked from the boat to the buoy in part A was root 41, okay? And the speed we just worked out to be 2 root 41. Well, the root 41s cancel and it just leaves with a half. And well, there we are. So that means we do indeed get my solution for time here of a half. So there we are. Cool. Let's have a look at some exam questions now. So I'm told in this question, a Coast Guard Station O, for origin, monitors the movements of a small boat. At 10 o'clock, the boat is at the point 4 minus 2 relative to the origin, and at 12:45, the boat is at the point minus 3i minus 5j relative to the origin. The motion of the boat is modelled as a particle moving in a straight line, constant speed, blah, blah, blah. You'll learn more about that sort of stuff in mechanics, but that's not going to be that... we're not going to really be caring about this sort of end sentence. It's just a bit of waffle for this particular section. So the first part says, calculate the bearing on which the boat is moving. So again, the common theme here, it's good to plot these points. So I'm told at 10 o'clock, it's 4i minus 2j. That's a position vector. That's a point, right? Because it's from the origin. If I then have the origin again, say here, just anywhere in space, origin there, 4i minus 2j, that's effectively going to be the point 4 minus 2, right? 4i minus 2j. So 4 across and then 2 down would be about there, right? I'll call that the point A, right? At point A. Then I'm told at this second point here, it's at minus 3, minus 5. As a point, we can say it's minus 3, minus 5. I'll call that point B. So again, from the origin, minus 3 would be to the left, right, by 3. And then down by 5, okay? And so I'm left with this point here. And so that I'll call that point B, right? So this is what I've got going on, okay? Yeah, so then if I then connect, so if I connect the 2 points then, A to B, oh, there we are. So basically the boat is travelling from point A to point B, right? So it's along this vector here, from A to B. So the bearing on which the boat is moving, well, it's moving along the line starting at A. So the bearing, if we measure the north line from A, it's going to be this whole angle here, right? Well, again, what we can do, well, actually, if I then split, well, I know that if I split again this line in terms of X and Y, the horizontal and vertical in this way, again, it's a common theme, right, of splitting things to X and Y, right? So again, this bearing here, well, overall, if this is going to be a right angle, right, 90, then I find this angle theta here, then I got the angle around the point again at 360. So if I take away 360 from 90 and theta, I get this bearing here, okay? This reflex angle for the bearing. So then I just need to find theta. But, so I've got this triangle, so this is going to be the change in X and change in Y. Well, again, the point A is 4 minus 2. And the B, over here, point B, is the point minus 3 minus 5. So I can easily then do the change in X, right? So how far along I'm going, so that direction, right? Sort of like the width, right? So, so I'm starting at 4 and then I'm at minus 3 for X. So overall I moved 7, right? Horizontally from to the left, right? From 4 to minus 3 is 7 that way. Likewise for Y, this height sort of thing then, well, I'm at minus 2 here for Y, and then I'm at minus 5 here for B. Overall I moved down by 3. Okay? So then then this is the right angle here. I can then again use SOHCAHTOA to find theta. And again, theta is opposite the length 3. So then tan theta is opposite of 3 divided by the adjacent 7. So therefore theta, if I compute that, I get 23.9198 blah 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 degrees. So therefore my bearing then here, my bearing is going to be 360. Take away the angle 90, the right angle, take away my theta of 23.198. And that will be 246.8 degrees to 1 decimal place. To 1 decimal place. Okay, cool. So that's part A done. Then part B then says calculate the speed of the boat. Right? So, speed. Well, the problem is now, you're probably thinking, well, magnitude of velocity like I'm usually doing. I don't have a velocity vector here, so I can't resort to doing that. So my other option is to simply use the formula, distance is speed times time. So speed would be distance over time, right? So then my problem is to find distance and time, right? Well, the distance, I'm given some times, right? Remember, I'm given some times here, 10 o'clock, 12:45, so I can work out my time. But firstly, my distance. Again, I'm moving from point A to point B. So isn't the distance again just going to be this hypotenuse here, right? Well then, can't I just do a bit of Pythagoras here to find the hypotenuse, the length from A to B? If I do that, then well, the hypotenuse, right, this length here, is going to be 7 squared and 3 squared, right? Pythagoras, right? So the distance is 7 squared. Well, the distance is going to be root 7 squared and 3 squared, right? So therefore, if I do that, I get root 58. Alternatively, if you're a bit uncomfortable with that, again, realise I have the point A, which is 4 minus 2, and the point B at the end, minus 3 minus 5. I could alternatively just simply use the distance formula to find the distance between these 2 points. But it works out to be the exact same way of just doing the Pythagoras of this triangle here. But either way, that's what we end up with in kilometres, is it? Kilometres? Yes, kilometres. Okay, lastly, we've got time. Well, I'm starting at 10 o'clock and I end at 12:45, right? So start at 10 o'clock and I end at point B at 12:45. Now, pay attention to the unit. What's it? Kilometres per hour. I need to convert to hours. So how many hours have I gone from start to end? Well, actually, that's going to be, so the duration or the time, that's going to be 2 hours and 45 minutes, right? But then I need it purely in hours. I need to convert this minutes to hours. Well, 45 minutes is hopefully recognised is going to be 3/4 of an hour, right? Remember, 15 minutes, 30 minutes, 45 minutes, and then the full 60. So it's going to be 2 and 0.75 hours overall, okay? And therefore that's my time. So then I can substitute that into my speed. So then distance is root 58 over my speed time, which is 2.75. If I put that in my calculator, I get 4 root 58 over 11, and as a number, that's 2.77, let's say, kilometers per hour to, let's say, 2 decimal places. Okay. The question doesn't specify to round it to, so it's best to leave it in exact form, but I also gave it as a rounded answer. Okay, you wouldn't lose marks for that unless I specified. You should leave it in exact form if you can, but if they specify to round it, then you must round it. But if you give the exact answer then round it, that's fine. If they don't specify. Okay, cool. Right. We've got this final question here. And here I'm now told relative to a fixed origin, I've got these 4 points here. okay, as vectors, as position vectors. I'm firstly told to show that AD is parallel to BC. So if I'm proving two vectors are parallel, we looked at this at the start of the chapter, there has to be multiples of each other. So AD has to be a multiple of BC. But firstly, I need to find what these two vectors are. Well, AD then, because we're already given the position vectors, so this is OA, this is OB, this is OC and OD. Remember, I can split up a vector in terms of position vectors by doing the second point, so OD, take away the first one, so OA. Well, OD is the vector 22, 24, right? Sorry. 22, 24, 22i, 24j. Take away OA, well, OA is just 12i. So it's 12i, but then there's no j, so it's 0j, so 0. If I do that calculation, I get, well, 22 take away 12 is 10, and 24 take away 0 is 24. Cool. And then need to find BC as well, right? And very similarly then, BC is going to be OC, take away OB. Well, OC as a vector is 50, 136. And then OB is going to be 16j. So there's no I, so it's 0i, so 0 and then 16 for j. And so there we are. If we compute that then, this subtraction, well, 50 take away 0 is 50, and 136 take away 16 is 120. So then these two vectors are parallel with their multiples. So consider this then. So this vector AD of 10, 24 has to be a multiple, so a multiple of k, let's say, of the vector, this vector here, 50, 120. Okay, can we spot what this multiplier will be? Well, you hopefully could spot it, but we could also just sort of solve it. So we could say that 10 has to equal 50k. So therefore k is 10 over 50, which should be a fifth, right? So does a fifth work? Well then, let's do a fifth times 50 is 10, and then a fifth times 120. So 120 divided by 5 does get me 24. Okay, so they are multiples. So they're multiples by a fifth here. So then we can say that AD, the left side vector, is a fifth of the vector BC. So therefore they're parallel. So AC is parallel to BC. No, so AD is parallel to BC, as they're multiples of each other. Or they're a multiple of each other. And there we are. Cool. Okay, then part B. We are told points A, B, C, and D are used to model the vertices of a running track in the shape of a quadrilateral. Runners complete one lap by running along all four sides of the track. The length of the sides are measured in meters. Given that a particular runner takes 5 minutes to complete 2 laps, find the speed. So again, we need to consider the speed. And again, we're not given anything about velocity. So we're probably going to have to resort to using speed is distance divided by time again. Okay. And I know I'm probably going to need to do that because the question gave me a time, right? It's, what was it? 5 minutes. So I am going to need speed as distance over time. So I'm going to need I'm going to need distance and time. Well, the time I can actually work out easily. It says 5 minutes for 2 laps. So I need to find the speed in that time. Well, the time is 5 minutes, but it's in the speed is kilometers per hour, right? So the speed is in kilometers per hour. So that means my distance needs to be in kilometers and my time in hours. Well, my time is in 5 minutes. The problem is I need my time in hours. So this needs to go to an hour. To convert that, well, we know that 1 minute, well, 60 minutes is 1 hour. So then you can scale it, like, right, some sort of ratio. We could then say 1 minute, to make it easy, is a 60th of an hour. And so therefore, if we divide by 60 to both sides, and then if I times by 5 minutes indeed would then be 5/60th of an hour. But that simplifies to, oh yeah, 5/60th of an hour. But 5/60th, 5/60, simplifies to a 12th. So 5 minutes is 1/12 hours. So cool. So that's my time dealt with. Now I just need my distance, and this is going to be the more trickier part. Okay. So I'm told that these 4 points A, B, C, and D are of a quadrilateral. They're the points of a quadrilateral here. Well, let's kind of plot them then. Well, we know it looks like a quadrilateral, but we're also told, remember, part A, AD is parallel to BC. These two are going to be sides of my parallelogram, quadrilateral, sorry. And one side is parallel to another. So I'm thinking that's probably going to be a trapezium, right? So AD is probably going to be, we're going to have 2 sides, right? On my trapezium. Remember, a trapezium looks like this. AD is probably going to be here, and BC is going to be here, right? It really doesn't matter actually how accurate your sketch is, or what the orientation is, or the sizing, or whatever. As long as you get a rough idea of where the labels go. So AD is parallel to BC, so that's where my sides are going to be, because it's going to resemble a trapezium. Because remember, a trapezium, one side is the opposite sides are parallel. Okay, which is what we proved in part A. So there we are, we got this sketch then. But if you wanted to be more accurate, you could plot these points in, these I and J points, as coordinates, and then you can measure it that way. It's completely up to you, but you don't need to spend much time worrying about how accurate your sketch is. But there we are, so AD, BC there. Now, we are then also told that runners complete 1 lap by running along all 4 tracks, all 4 sides of the track. Well, hang on a minute then. If we can work out the vectors of each side, then we can find the magnitude and therefore all the sides. That will then give me the distance of the lap, right, by adding them all together. Let's do that then. I'll do that up here. Right, I'll do it up here. Let's go down to the question. So, firstly, I've already found the side AD, right? The side AD on my shape, it's 1024, right? So therefore, the length of AD, so the magnitude of AD, is going to be root 10 squared at 24 squared, which would be 26. 26. Okay. What are the units? Meters. Okay, meters. Then I also found the side BC in my answer to part A. As a reminder, BC was 50, 120. So therefore the length of BC is going to be root 50 squared add 120 squared, which would be 130 meters. Right, so that's these 2 sides dealt with. So AD and BC. Now I need to find the other 2 sides, right? AB and CD, these 2 sides. Well, then the vector AB, then I can find that vector by doing OB take away OA. So that would be, well, OB, the vector is 0, 16. And then OA is going to be 12i, so 12, 0. If I do that calculation, I get minus 12 and then 16. Cool. So therefore the length of AB is going to be root minus 12 squared as 16 squared, which would be 20. Cool, 20 meters there. I can add these on then if I wanted to. So A on my diagram, so AD is 26 meters. 26 meters, so 26. BC was 130. AB was 20. So then I just need to find CD. So CD then, so that's going to be OD, take away OC. So OD, the vector D was 22, 24. Take away OC. Now OC was 50 and 136. If I do that, I get, well, 22 take away 50 is minus 28. And 24 take away 136 is minus 112. So therefore the length of of CD is going to be root minus 28 squared at minus 112 squared, which would be 28 root 17 meters. Okay, 28 root 17. So now I've got all my sides. So therefore then, if we go back to the question, the runners complete one lap by running along all four sides. So the distance of one lap then, it's going to be all these four sides added, right? I'll do it down here. So distance of one lap. That's going to be, what are my sides? 130, 20 and 26. Add my 28 root 17. If I do that, then I get 291.446 blah blah blah, and that would be in meters, right? But that's one lap. If you then remember, we are told a particular runner here takes 5 minutes for 2 laps. So we found the distance of one lap, so 2 laps is just going to be double this, right? So therefore, distance is going to be 2 times 291.446, which should be, if I times that by 2 then, I get 582.893 blah 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 meters. But again, we then need to pay attention to our units. Speed is kilometers per hour, so the distance needs to be in kilometers. So then you should remember, to get from meters to kilometers, we need to divide by 1,000. Because remember, a kilometer is a kilo is 1,000, kilometer is 1,000 meters. So divide by 1,000. If we divide that by 1,000, we get 0.582 blah 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 kilometers, and that is my distance then. So if we go back to our speed then, our distance is 0.582 blah 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 divided by time, so it's going to be over time. Now our time is 1/12. That obviously a fraction and a fraction looks nasty, but remember this is just saying 0.582 divided by 1/12, right? So if we do that in our calculator, we get 6.994 blah 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 kilometers per hour. Okay. We could round it, probably say to 7, right? 7.0 kilometers to nearest decimal place. But actually the question didn't specify to round it, so we're fine if we round it to whatever we want. But that is our answer then. Cool. So yeah, that is vectors. So again, 2 key takeaways. Find it can be helpful to find the magnitude of find the magnitude if you're dealing with vectors and shape and sides, and also to consider splitting a vector, right? A vector like this, say if we had 3i add 2j, to consider maybe the x part of 3 and the y part of 2, right? It might be helpful to find a vector to split it into the x and the y part, or the I and j part, right? In that way. And obviously again, so yeah, and so that's vectors, but I'll see you next time.